So now we're going to talk about one of the most sort of straightforward ways to fit a model and to sort of make your model reflect what we're seeing in reality and data, and that is the fitting of an exponential growth model. So why would we fit an exponential growth model? The good news is that early in an epidemic, without interventions, vaccines, people responding to it, the growth of an epidemic should be exponential. It should follow an exponential curve. Mac Hyman at some point, who's a modeler at Tulane, was talking to me about this at some point, and his sort of statement on this is, very early in an epidemic, fitting a model to data is very, very easy. All you need is a straight edge and some log scale graph paper. Later, it becomes much more difficult, but in this very early stage, which is often when people are sort of most interested in getting very fast estimates of things like the basic reproductive number and things like that, you can get this fairly straightforward. And essentially what you can do is you can look at this relationship that we have an equation here, which is that the current case counts, so CT, so for the cases at any given point in time, equals the number of initial cases. So you can set this to be a constant of whatever you think is appropriate. And then E to RT, which is R is what we're trying to estimate. That's the growth rate, and then time. So the good news is this is very easy to estimate. If you can plot your data on the log scale and draw a line, essentially just what Max suggested, the slope of that line is R. So that's your growth rate. If you have the doubling time, so the time it took you to go from 50 cases to 100 cases, 100 cases to 200 cases, doubling time equals the natural log of 2 over R. So you can back calculate that growth rate even if you just know the doubling time. So you can get a lot of information out of a very simple case time series. And the appeal of this is exactly that. You don't need a lot of sophisticated modeling. Megan and Becky are going to talk about some much more sophisticated ways of fitting data later. You don't need to do those for this method. You only need cases over time, and you can theoretically fit the growth rate. And then if you know the growth rate and the generation time, so that is the time between the infection time of a primary case and one of its secondary cases, which is often approximated by a serial interval, although using a serial interval can result in some bias here, you know R naught. So the approximate relationship there is the growth rate equals R naught minus 1 over T. So you can take that information, and this is how you get modeling groups that produce very fast estimates of R naught in an epidemic. So you'll occasionally see groups that, maybe a week into the epidemic already have an estimate for R naught. And that's how they're obtaining this, is they're getting that information just from the growth rate at this particular point in time. So there are, however, a number of problems with this method. So the assumption here is that R is constant, which is only really valid early in an epidemic. So we're assuming you're on this exponential growth sort of pathway, and that's really only true very, very early on. It's one of those sort of ways it links to R naught is also only true sort of very, very early on. If you think about the definition of R naught, it's the number of cases created by a single case dropped into a fully susceptible population. That's a very early epidemic process. But because you're early in an epidemic, it's also very stochastic. There's a lot of noise in your data. So if you're trying to fit this growth rate using sort of a statistical approach, this can cause problems. There's often a very strong desire to use something very simple and very accessible, something like least squares to fit R. So the example I used where you sort of plot all your dots and you sort of draw a line through them, the sort of computational approach to that is least squares. You can have a lot of problems with that depending on sort of at what point in time you're trying to estimate that growth rate. It gets influenced by sort of outlying points as you deal with stochastic noise. There are more sophisticated approaches to this, but even they are still trying to fit this exponential growth sort of regime. And so they have struggled with the next problem, which is that the moment there's any intervention that should move the epidemic off an exponential growth trajectory, so social distancing, a vaccine, emergent behaviors by people as like public health campaigns start taking place and people start, changing their own behavior, this stops being a reliable approach. And what that also means is this is potentially sort of a non-viable approach for whole swaths of infectious diseases. Anything that's not in that early emerging phase. So you see a lot of interest in things like the serial interval, the growth rate, generation time, things like that. When you're talking about emerging infectious diseases, when you're talking about sort of the field of epidemiology that's sometimes called outbreak science, that is only one part of the infectious disease modeling world. And if you're interested a lot in endemic diseases or diseases that aren't on that sort of exponential growth curve, this method sort of can't apply. Whereas some more sophisticated methods that require a lot more knowledge and potentially a lot more parameter fitting may. So that's exponential growth fitting, and I'll see you in the next lecture.